Good morning, everybody. Today we are going to be looking at 3.6. Keep in mind, after this one we have Tuesday and Wednesday, and then we will be releasing the test probably on Thursday, no later than Friday, to be completed by midnight on Tuesday of next week. So again, we're looking at 3.6 confidence intervals for one population proportion. Now remember, a proportion is simply just another fancy statistical term for percentage. Sometimes when we talk about proportions and attributes that we're looking for, a few examples might include the percentage of U.S. adults who have health insurance, percentage of cars in the U.S. that are imports, the percentage of U.S. adults who favor stricter clean air standards, or the percentage of Canadian women in the labor force. I know a lot of our problems focus on Americans, but we ought to keep in mind there's other countries in the world too that they have populations, and so maybe we want to look at some of their percentages as well. Anyway, we'll go ahead and just start with example 1. It just says that many employers are concerned about the problem of employees who call in sick when they are not ill. The Hilton Hotels Corporation commissioned a survey to investigate that issue. One question asked the respondents whether they call in sick at least once a year when they simply need time to relax or just play hooky. So the survey polled 1,010 randomly selected U.S. employees. The proportion of those employees who play hooky was used to estimate the proportion of all U.S. employees who play hooky. So really what we're going to do in this example is just discuss the notation. We're not really solving a problem per se. We're just discussing the notation that we use. So for our purposes, we are going to use a couple of different notations. There's going to be some new notation introduced here. But the variable, or not the variable, but P, a lowercase p, represents the proportion. Whoa, I can't spell this morning. Of all U.S. adults or U.S. employees. That's the key there. This is all U.S. employees. Who play hooky. The who play hooky is our attribute that we are testing. So we want to make sure we understand what that means as well. Play hooky. And that represents the population. And typically that's a parameter. Remember, a parameter always represents a population. So it's really going to be a value that's estimated. The proportion of the sampled employees, we use a different notation. It's still the lowercase p, but we put this little hat over it, and it's actually called p hat. And that is the proportion of sampled U.S. employees who play hooky. And the difference between these two is that P is a fixed number, whereas P hat is a variable. P hat can change based upon our samples and the responses that we receive from those samples. For example, we may have in a given sample, we may have that 202 employees say that they play hooky. And it's the same way we calculate any other percentage. It's the part over the whole. So we sampled 1,010 employees. 202 of them responded that they played hooky. So that's going to be 0.20 or 20%. Okay, that's our variable. And then we use that variable to estimate the population proportion. Another example might be, let's say that we had 184 of those employees that were surveyed said that they played hooky. So then we would end up with a new value. That's why it's a variable, because it does change from sample to sample. And we would come up with 18.2%. So the notation is what we wanted to get comfortable with here in example 1. P is the population proportion. That's a parameter. It's a fixed value. And then P hat is the proportion of the sample population. So here's the more precise definitions for those two values. Population proportion is P. That's the percentage of the entire population with the specified attribute, and P hat is the percentage of the sample that has the specified attribute. So remember, the attribute in the previous example was who played hooky, and a sample proportion is simply computed by dividing X by N, where X represents the number of members in the sample that have the desired attribute, and N is the sample size. For the sampling distribution of the sample proportion, this is something we want to focus on right here. The mean of P hat is equal to the population proportion. So the mean of P hat equals the population proportion. The standard deviation of P hat is going to be the square root of P times 1 minus P divided by N. And that is illustrated right here. Whoops. Here. And P hat is approximately normally distributed for large values of N. So for a large sample size, we would expect P hat to be normally distributed. The confidence interval procedure for P, we have to first assume it's a simple random sample, and that the number of successes and the number of failures are both going to be greater than 5. So a failure is when we have a number of the sample that has the attribute we are looking for. Then the failures are the portion of the sample that does not have the attribute we are looking for. So for a confidence interval of 1 minus alpha, we're going to use the table to find z sub alpha over 2. Confidence interval for P is going to be P hat minus z sub alpha over 2 times the square root of P hat times 1 minus P hat divided by N. And then we also do the same thing by adding, because it's going to be that plus minus when we talk about a confidence interval. Remember, confidence interval is a range. And we're going to put that into practice here with example 2. We're still talking about the same example. We refer back to this one throughout the duration of this set of notes. 202, but now we do have a number of employees who did respond that they have played hooky. So we have 202 employees who play hooky. We want to find a confidence interval of 95% of all U.S. employees who play hooky. So what we want to look at first is our attribute is, again, plays hooky. Our sample size is 1,010. The number of employees who play hooky that were surveyed is equal to 202, so that's our value for X. And we have to check N minus X to verify that this also is greater than 5. Remember, that was one of our assumptions in the box above. So we have 1,010 minus 202, which does equal 808. So X is greater than 5, N minus X is greater than 5. So we can go ahead and proceed with the steps that were outlined in the notes above. So the confidence level we have to set up first, and we know we're looking at 95%. And when we do this for our purposes, we need a 95% confidence interval, which means that alpha is equal to 0.05. Remember, that's 1 minus 0.95 equals 0.05. That's how we came up with alpha. And we have to look at z sub alpha over 2. And I'm not going to refer back to the table. We've had plenty of practice with the table now, but unless you guys need clarification, just let me know. So this is going to be z sub 0.05 over 2, which is equal to z sub 0.025. And remember that z-score is what is the z value that has an area of 0.025 to its right, which similarly corresponds to the z value that has 0.975 to its left. And we will find that that z-score is 1.96. Remember, the z-table is always giving values to the left, never to the right, but the z subnotation is looking at the area to the right. So now we have to establish our confidence interval. So here we will do the confidence interval. And remember, the confidence interval is p hat plus or minus z sub alpha over 2 times the square root of p hat times 1 minus p hat over n. And we just substitute in what we know. One thing that we did not calculate up here at the top that I forgot to write down is our p hat value. P hat is the sample with our attribute divided by the sample size, and that's going to be equal to 0.2 or 20%. So we know all of our values that we need to use to evaluate the confidence interval, and we're just going to substitute. So our p hat is 0.2 plus or minus our z-score that we computed in the previous step is 1.96. And then we just substitute in our p hat again, 0.2, 1 minus 0.2, divided by our n, which is 1010. And when we type this in the calculator, we end up finding that we have either 0.175, that's the 0.2 minus 1.96 times the square root, to 0.225, and that's the 0.2 plus 1.96 times the square root. So there's our confidence interval. And what this means as far as the interpretation goes is that we can be 95% confident that the percentage of all U.S. employees who play hooky is somewhere between 17.5 and 22.5%. And that's all that the confidence interval means when we evaluate that. The margin of error was the portion of that long equation we had earlier, where it was p hat plus or minus z sub alpha over 2 times the square root. Well, the margin of error is just the portion that's after the plus or minus, just like it has been in the past. That's our margin of error. It gives us the tolerance, the range that we're within on any given problem. So, for example, 2, I've kind of highlighted that right here. The margin of error was 0.025, and we end up coming up with the same values, but it ends up being it's plus or minus 2.5 percentage points to the left, or plus or minus 2.5 percentage points to the right. And if you look at our calculations in example 2, that is exactly a 5% difference between the lower bound and the upper bound. So 2.5 to the left of whatever the middle value happens to be, 2.5 to the right of that middle value. So determining the required sample size. So sometimes we need to, we've talked about this as well, we want to come up with a certain degree of confidence, and we already have that in advance. So we need to take that degree of confidence, and we need to make sure that we take a sample size, a large enough sample size to meet that degree of confidence. And that equation is given right here. Make sure my highlighter's on. It's we've taken the previous equation, we've solved it for n. We've taken the margin of error and we've solved that for n. So it's just going to end up being p hat times 1 minus p hat times z sub alpha over 2 over the margin of error quantity squared. And the issue that we run into with that is we don't know the sample proportion because we're trying to come up with the sample size. So we have to come up with a way of estimating what p hat may be. So the graph that you see here on the screen, I've graphed p hat times 1 minus p hat compared to p hat. So p hat was kind of like my x. Y is p hat times 1 minus p hat. It ends up being quadratic in nature, and you can see that we have this vertex at 0.5 and 0.25, and that is important because the largest value, let's see if I can get this on the same screen. I'm looking at this section right here. The largest value reveals that the largest p hat times 1 minus p hat can be is 0.25, which only occurs when p hat is 0.5. So the further p hat is from 0.5, the smaller the value of p hat times 1 minus p hat will be. And I'm sure you're already tired of hearing me say p hat so many times. But because the largest value of that is 0.25, the most conservative approach for determining the sample size is to use that value in the equation for n. So we're just going to use that 0.25 in our equation, and it's going to generate a sample size much larger than we traditionally need, but it will at least guarantee that we meet that margin of error that we're looking for. Another thing is we could do the educated guess. And I'm just going to go down here to the red box where we talk about that. We have the confidence level. We can make an educated guess, and we're going to call that p hat sub g for guess. And we just make that educated guess based off the information that's provided, and we're going to apply that shortly, and you'll see what we're talking about. And here we are with example 3, and it's still talking about the U.S. employees who play hooky, and we're going to kind of look at this determining sample sizes based off what we just saw prior to this example. So it says first to obtain a sample size that will ensure a margin of error of at most 0.1 for a 95% confidence interval. So we have to identify two things. We have to identify the value for z sub alpha over 2, which we already know from our previous work, but I'm going to go ahead and write this in anyway. And we also need to compute our margin of error. We need to figure out what the margin of error is going to be, and that is given to us at 0.01. So we need to find a sample size that will guarantee us a margin of error of at most 0.1 for a 95% confidence interval. So using the equation illustrated for n earlier, we have n equals 0.25. So we're not using the guess, we're using the maximum value found on that graph. It's 0.25 times z sub alpha over 2 over e quantity squared, and we substitute in the values that we've just computed for z sub alpha over 2 and e. That's 0, 1, not 1. And when we simplify that, we get 9,604. We always want to round up. So if we take a sample size of 9,604 U.S. employees, the margin of error will be 0.1 or less, based off the information that we're seeking. So we would have to survey 9,604 U.S. employees to meet the criteria of being within 1 percentage point plus or minus for 95% confidence. The part B, it says find a 95% confidence interval for P if for a sample of the size determined in part A, the proportion of those who play hooky is 0.194. So here we're assuming that our population, or that our sample, is what we found in part A, which is 9,604. So we have a couple of values that we want to make sure we write out first. Alpha is 0.05. Our n is 9,604. That's our sample size. We know that p hat is 0.194, and we're looking for a 95% confidence interval. So it's going to have the endpoints we have all the information we need. It's going to have these endpoints at 0.194 plus or minus our z sub alpha over 2 times the square root of p hat times 1 minus p hat divided by our sample size. And when we type that in, we get that our confidence interval is from 0.186 to 0.202. So based on a sample size of 9,604 U.S. employees, we can be 95% confident that the percentage of all U.S. employees who play hooky is somewhere between 18.6 and 20.2%. The margin of error for part B is 0.08, and we know that because if you take this 1.96, just this 1.96 times what's in the parentheses, we get a margin of error 0.008, and that is significantly less than the margin of error that we wanted in part A. And we shouldn't be surprised by that, because we used that maximum value from the parabola that we looked at earlier, and I mentioned that will give you a much larger sample size than necessary. So it in this case we did end up with a much less margin of error than what we anticipated, but it does meet the criteria of what we were looking for. So that was the answer to part C. For part D, we are going to repeat A through C. If the proportion of those sampled who play hooky can be reasonably presumed to be between 0.1 and 0.3. So here we're looking at our guess, and this is where we were talking about using an educated guess. So because our range on that parabola was from 0.0 to our vertex, which was at 0.5. Remember, we said anything close to the vertex is going to be a better reasonable guess. In our case right here, since we're talking about 0.1 and 0.3, 0.3 is the closest value to 0.5. So we're going to use that as our guess. So we have p hat sub g is equal to 0.3. It's whichever one of your educated guess values is closest to 0.5. And then that's going to help us to determine the sample size. So here we have n is equal to p hat sub g times 1 minus p hat sub g over z sub alpha over 2 over a margin of error, quantity squared. So we substitute in our known values, 0.3, 1 minus 0.3, 1.96, margin of error 0.01, quantity squared. When we type that in and we round up, we get a sample size of 8,068. So there's our sample size. So with alpha being 0.05, and n being 8,068, and we have p hat is 0.194. We can find the 95% confidence interval by substituting those values in. So we have 0.194 plus or minus 1.96, that's our z sub alpha over 2, 0.194, and then we divide that by our sample size of 8,068, and we get that it is plus or minus 0.194, 0.194 plus or minus that value, which is 0.09, which is going to be 0.185 to 0.203. So what that tells us is that based off a survey or a sample of 8,068 U.S. employees, we can be 95% confident that the percentage of all U.S. employees who play hooky is somewhere between 18.5% and 20.3%. And the margin of error for this estimate is going to be 0.009. Again, the margin of error is just the simplification of what I've highlighted there in pink. So if we compare the results from A through C to those obtained in Part D, we notice that by using the educated guess, we reduced the required size, and only 0.1% of our accuracy was lost. So the margin of error rose a little bit, but it was still less than the 0.001 that we were, or 0.01 that we were looking for. So by taking this educated guess, we reduced the work required because we've sampled 1,500 fewer employees, and we still met the tolerance for our margin of error and our confidence interval. So that's all you really have to look at when you're talking about comparing these two results. One, for Part A, we didn't use the guess. We used that 0.25. For the Part D, we used the guess method. We reduced our sample size significantly, which, if this was a practical application, would reduce the required work by a large amount. And we were still within the tolerance levels of what we were hoping for, of a margin of error of 0.01 with a 95% confidence interval. So this is simply just going to be a matter of using the formulas correctly and substituting, typing in into your calculator, and just being careful about how you enter these. So there's your homework problems. There are 6 of them. Yes, I know. There's parts A through F on number 6. Oh my gosh, I'm a tyrant. But again, if you guys have questions, just remember to ask me, shoot me a message. I'll be happy to answer it. And I hope everybody is doing wonderful today.